Welcome you all once again in this lecture on separable spaces. So, yesterday we have discussed the dense set, countable dense set, and several characterizations and some exercises. And today we will discuss the separable metric space. So, if a metric space has a countable dense set, then it is called a separable space. That is, a metric space X is said to be separable if there exists a countable dense set in X. Now, we have seen in the previous talk that the real line has a countable dense set, that is your set of all rational numbers or set of all irrational numbers. So, set of all rational numbers is a countable dense set in R. Okay, and therefore R is a separable metric space. So, a metric space X is said to be separable if there exists a countable dense set in X. A metric space which is not separable is called inseparable. As I mentioned that yesterday we have seen that the set of all rational numbers Q is dense in R, and of course Q is countable. So, Q is countable dense subset of R, so R is separable. Similarly, we have also seen yesterday that the set A of this form, okay, where A and B are rational numbers, this is a countable dense set in C, and therefore C, set of all complex numbers, is separable. We have also seen that Rn is separable because the Qn, which is the Q cross Q cross Q n times, is countable and it is dense in Rn. So, C, R, Rn are separable metric spaces. Okay. Now, let's take another example. As you might be remembering that we have seen that if we are considering the LP space where P lies between P is greater than or equal to 1 and strictly less than infinity, okay, and we consider A is the set consisting the point of this form A1, A2, An, and after An all entries are 0 and all the Ans are rational numbers, okay, then we have seen that this set A is dense in LP space, but it is also countable. That you can see that if An denotes the subset of all those elements X which of the form that Ai's where I runs from 1 to infinity, such that Aj is equal to 0 for all j is equal to greater than or equal to I plus 1. That is to say X, so up to A1, A2, An are non-zero or maybe some of them 0, but after that all the entries are 0. Then An is countable, and so the A, this A which is equal to the union of An. So A is a countable dense subset of LP space, and therefore LP space is separable. Now we have the space CAB, set of all continuous real valued functions defined on the closed interval AB. As we have seen yesterday that PAB, that is the set of all polynomials defined on AB with rational coefficients, is dense set in CAB, and it is not only dense but it is also countable, and therefore CAB has a countable dense set, and therefore CAB is separable. Now we have seen that the discrete metric space has a dense set, and which is if X is countable. So a discrete metric space is separable if and only if X is countable. Now let us see an example of an inseparable space. So if we consider the L infinity, that is the space of all bounded sequences of real or complex numbers with the metric defined in this way, that is to say with the sup matrix, then this L infinity is not a separable space. So you have to prove that this set is not separable. It means that there is the LP space does not have any countable dense set. Okay. So what we will prove that? We will prove that if suppose there is a countable dense subset of L infinity, and then we will prove that we will have a contradiction. So for that we consider a subset A of L infinity such that the entries of the sequences xn is equal to 0 or 1, and therefore of course all these sequences are bounded, okay, because the entries are 0 and 1. Okay, now we claim that A is uncountable. So this kind of the set is uncountable. So if B is any countable subset of A, then the elements of B can be arranged in a sequence S1, S2, Sn. So keep in mind these are the sequences. Okay, we construct a sequence S as follows. Okay, if the mth element of the sequence Sm, so keep in mind these are the sequences. So mth element of Sm is 1. Then the mth element of S of this sequence which we are constructing is 0. So if the mth term of this sequence is 1, then the mth element of the sequence X is 0 and vice versa. Then the element S of X differs from each Sm in the mth place, and it is therefore equal to none of them. So X cannot be in B. Okay, although S in A. This shows that any countable subset of A must be a proper subset of A. It follows that A must be uncountable. For if it were to be countable, then it would have to be a proper subset of itself, which is absurd. We produce to use the uncountability of the subset A to argue that L infinity must be inseparable. Okay, the distance between two distinct elements X and Y of A is equal to this thing. Okay, this is by definition. And now because the distance is what? Distance is the supremum of dxy, but the elements of A consist 0 or 1. So the distance, the supremum of this is equal to 1. Suppose contrary that E is a countable dense subset of E infinity. Okay. Suppose A is a countable dense subset of infinity. In other words, we are assuming that L infinity is a separable space. Then consider the sphere of radii 1 over 3 whose centers at the points of E. Then their union is the entire space L infinity, because E is dense and in particular contains A. Since the spheres are countable in numbers while A is not, in at least one sphere there must be two distinct elements x and y of A. Let x naught denote the center of such a sphere. Then the distance dxy is equal to 1, which is less than or equal to this thing, dx x naught plus dx naught y, by using the triangular inequality, and this is less than 1 over 3, this is less than 1 over 3, so the whole is less than 1. So 1 is less than 1 is a contradiction, and therefore our assumption, our supposition that E is a countable dense subset of infinity, L infinity, is absurd. It is not possible, and therefore L infinity with respect to this metric T is not a separable space. Okay, so we have seen that the definition of a separable space and several examples of separable space and examples of inseparable space. So very simply we can see that the set of all real numbers, set of all complex numbers Rn and Cab all are separable metric spaces, while L infinity, that is a set of all bounded sequences of real or complex numbers with respect to the submetric is not a separable space. It means that it is unseparable space. Now, suppose if y is a subset of x and xd is a separable space, can we say that y is also separable with respect to the induced topology? Yes, and that we will prove in our next theorem. So our theorem says that let xd be a metric space and y be a non-empty subset of x. If x is separable, then so is y with respect to the induced metric. The proof is again we can see that let us take S is equal to the set of sequence xn be a countable dense subset of x. Okay, so this is a set of points x1, x2, xn and so on for all n in n. And if S is contained in y, then there is nothing to prove, because as we are assuming that is the countable dense set, and countable dense set, if it is it may be in S and may not be in, it may be in y and may not be in y, because y is a subset of x. So if S is in y, then it means that y has a countable dense set and then y is separable, so there is nothing to prove. So in other case, we construct a countable dense subset of y whose points are arbitrary close to those of S. For positive integers m and k, let Smk is equal to S1 over k xm. That is to say, Smk is an open sphere with center at xm and radius 1 over k. And choose ymk in and choose, because this is your non-empty, so we can choose an element ymk in this open sphere, but only this, because this open sphere is in x. And now if you take the intersection of this open sphere with y, then this open sphere in Y. So we are choosing YMK in this open sphere whenever this set is non-empty. Then of course dxm ymk is less than 1 over k, because xm is the center, ymk is an element of the open sphere whose radius is 1 over k. So this distance is less than 1 over k. Now we claim that the countable set A is equal to countable subset of A is equal to ymk such that m and k are positive integers. Okay, so we assume that the subset A of Y is dense in Y. Okay, for that let Y is in capital Y and epsilon greater than 0 be given. Let k be so large such that 1 over k is less than epsilon by 2, and find xm in S1 over k y. Okay, then from the definition of the open sphere, dy xm is less than 1 over k, and of course y lies in smk intersection y. Then we can see that dy ymk is less than or equal to dy xm plus dxm plus ymk by using the triangle inequality. And this is less than 1 over k, this is less than 1 over k. So, but now we have assuming that 1 over k is less than epsilon by 2. So, this is less than epsilon by 2, this is less than epsilon by 2. So, this is equal to epsilon. That is to say, this is less than epsilon by 2. It means what? It means that ymk lies in an open sphere with center at y and radius as epsilon. Since y lies in k and epsilon, since y and epsilon were arbitrary, it follows that y lies in the closure of A, and hence the closure of A is equal to y, and thus A is the countable dense in Y, and therefore Y has a countable dense subset of Y, and so Y is separable. Now we have a characterization of a separable metric space in terms of second countable space. Okay, so for the second countable space, I go back. Let me recall the definition of the second countable space. Go back. Here is a metric space X. A metric space X a metric space X is said to be first countable. No, we have to see the second countable space. So, a metric space X is said to be second countable if there exists a countable base for the family of all open subsets of X. Okay, so we have to prove that it has a countable base. It has a countable base for family of open subsets of X. So, X is separable if and only if it is a second countable. Suppose that XD is a separable space and A is the set consisting A and is in natural numbers, be a countable dense subset of X. Consider a countable collection of open spheres. This is S1 over K Aj, where J, K are natural numbers. Okay, with centers at Aj and radii Rk is equal to 1 over K are rationals. So K and Aj are rational numbers. Then this family we see is your countable family. That is, we are taking the B is equal to the open spheres, okay, with center at Aj and radius Ri, where Ri is a rational number. Okay, then we claim that B is a base for the family of open subsets in X. So let G be an open set in X and X is in G. Then for every epsilon positive, then for some R is greater than 0, SRX is the subset of G. Choose a positive integer m such that 1 over m is less than R upon 2. Since A is dense in X, there exists Aj in A such that Aj lies in the open sphere with center at X and radius 1 over m. That is, the distance between X and Aj is less than 1 over m. And now we show that the open sphere with center at Aj and radius 1 over m is a subset of the open sphere with center at X and radius r. So for that, let us take an element y in this set and we will prove that it lies in this one. That is to say, we have to prove that dxy is less than r. So from here, because y lies in the open sphere Aj with radius 1 over m, that dAjy is less than 1 over m. And now by using the triangle inequality, we see that dxy is less than or equal to dxaj plus dAjy. But this is less than or equal to, this is strictly less than 1 over m, this is strictly less than 1 over m. So the whole thing is equal to 2 over m. But 2 over m, from here we can see that it is less than r. So dxy is less than r. It means that y lies in the open sphere with center at X and radius r, and hence this is a subset of this one. So this is holds good. Now also X is an element of the open sphere with center at Aj and radius 1 over m, and thus for every point X in G there exists an open sphere, okay, in the family this containing X and contained in G. Okay, hence G is a countable base for the family of all open subsets of X, and therefore X is a second countable space, okay, by using the characterization of a countable base by using the definition of the base. Now to prove the converse part, that is to prove that if a metric space X is second countable, then it is separable. So assume that X is a second countable space, okay, and let B is equal to, B is the set of elements Bn, be a countable base for the family of all open subsets of X. For each n, we choose a point Bn in Bn, and let A the set consisting Bn in small bn and capital Bn. Then we see that A is countable, and now we will show that the closure of A is equal to X, and which will imply that the set A is dense in X and A is countable, and therefore X has a countable dense set and therefore it is separable. So let X in capital X be arbitrary and G be any open set containing X. Since B is a base, there exists at least one element B and not in B such that X is in B and not, and which is a subset of G. From the definition of A, we have B and not is an element of A for all B and not in B and not. Therefore, G contains a point of A other than X. It means what? It means that X is a limit point of A, and therefore X lies in the closure of A. And so, what we have taken? We have taken that X was our arbitrary point. So we have taken X was arbitrary. This means that the closure of closure of A is a subset of X. X is a subset of closure of A, and therefore closure of A is equal to X. And hence X has a countable dense set, and therefore it is separable by the definition. Okay. So here is again I have given several exercises. So suppose you have the set S of this form where A and B are rational numbers, be such that A is less than, then prove that there exists an element S in S such that this is holds good. Okay. In other words, S is dense in R. Okay, so the proof is given here. I am not going to explain this proof, but you try to prove this by yourself first, and then if you are failed to prove, then you can see the proof over here. I have also given several other exercises which you can prove very easily. And now here is basically I would like to mention this one, that if A is a non-empty subset of a metric space X, then the following statements are equivalent. That is to say, A is dense in X, the only closed superset of A is X, the only open set disjoint from A is empty, A intersects every non-empty open set, A intersects every open sphere. Okay, so these are equivalent, you can say, the definitions of a dense set, which you can prove very easily. Now, if Gn be a sequence of dense open sets in a complete metric space, then prove that their union is also dense. Of course, there are several other exercises, but here I would like to mention that if X is a metric space, Y is a subset of X. If Y is separable and the closure of Y is equal to X, so, okay. So here is you cannot, if and the closure of Y is equal to X, it means that Y is separable dense subset of X, then X is separable. Otherwise, it is not. Try to find out what will happen if we relax this assumption that the closure of Y is equal to X. That is, if Y is not dense set, then whether we can say that every subset of a separable of a separable space is separable. So here we have the proof, you can see. Now I come to the another one. Okay, so I stop over here this talk, and we will see next talk tomorrow. Okay, thank you very much.